fractions, like separating fractions into partial fractions.
Ah, partial fractions.
Mm-hmm.
Okay. Those are all.
So I've got a couple problems
Okay.
that I need help with that are hard.
Okay. I haven't done partial fractions in a while. I know I can do the easy ones, and I think I know how to do some of the harder ones. What do you got?
Okay, so the first one is x squared minus 1 over x times x squared plus 1.
Boy, you weren't kidding.
And she taught us how to like separate these.
I know how.
So,
Yeah, the easy ones are really easy to do. We
mm-hmm.
can try that method. Let's see. So I want sum A over X.
Yep.
Sum B over X squared plus 1.
She put for quadratic functions you want bx plus c.
Plus C. Okay, that's where I'm. Like I said, it's been a while on the harder ones. Okay.
Mm-hmm. No worries.
Yeah, I think we can make do with this though. Because now we know that if we try to add those together to get, with that common denominator, then what we're going to have is A times x squared plus 1 plus x times bx plus c. And now we know that that combination has to be equal to this numerator, right? Because if I add those together, I end up with that as a common denominator. And so I know the numerators have to be equal to one another. And so we need to solve that. Now, let's see. There's a technique that you use on the simpler ones for solving these that's probably a little bit easier. Maybe not. Let's expand this out.
So it expands out to be ax squared plus bx squared plus cx plus a.
Okay. And then we can factor the x squareds out and giving that a coefficient of a plus b. And we've only got one x term, and we've got a constant. Did I do that right?
Yes.
And now, since that has to be equal to x squared minus 1, then we know that a plus b has to equal 1. See why?
Okay. Yeah,
C has to equal 0 because there is no x term.
Okay, yeah.
And A has to equal minus 1, which means if A is minus 1, B is 2.
A plus, okay.
That equation there. Okay, so now let's test and see if we got it right. Okay, that's really the proof in the pudding here. So A was minus 1. B was 2. And C was 0. So here, So that's what we think it is, right?
Yeah.
Okay, now let's check it. In other words, if I were to try to add those two fractions together, I would have an x times x squared plus 1 plus x times x squared plus 1. This must be minus x squared plus 1 so that I don't change the fraction.
Okay.
I always do it like that. Well, hold on. Did I do it right?
Um,
No, I got to have a parentheses around that.
yeah.
And over here, it's for it to end up being 2x up there, then it's got to be 2x squared.
Okay.
And now, this fraction should be exactly the same as that fraction. I can cancel the x squared plus 1. I got minus 1 over x, so it is. This fraction
Mhm.
has to be exactly the same as this fraction, and cancel out an x, and I end up with 2x over x squared plus 1.
Okay, yeah.
We got it. A is minus 1, B is 2, C is 0.
Cool. All right. Another one of those. This one's a little bit harder.
Wonderful. Okay.
Yeah. So this one is x over x to the third minus x squared minus 2x plus 2.
Notice what we
So,
have in the bottom. This actually is going to be an easier one because
okay.
you don't end up with an irreducible quadratic. What made the last one hard was the fact that the denominator had an irreducible quadratic. Okay?
Okay.
So this, you'll notice, can be solved by grouping.
Oh, okay. So you can go to,
Is that the same as what my denominator is?
yes.
And notice what I had to do. I had to change the sign to minus 2. That's
Mm-hmm.
the most common mistake that every student I have is going to make on this kind of a problem. Because I can't just add parentheses to the right two terms and add parentheses to the left two terms. Because this is subtraction going on there, it's not going to be the same if we
Okay.
add parentheses, okay? Now, what's the greatest common factor in this two terms here?
X minus 1.
X squared is the greatest common
Oh,
factor.
x squared for the first one.
X minus 1.
Okay, yeah.
And over here, what can I factor out?
Negative 1.
A 2.
So minus 1. Oh, a 2, sorry.
Okay, a positive or a positive 2 is what I'm going to divide. In other words, this is what I'm going to do. I'm going to divide that term by 2 and that term by 2. That's what you do when you factor something out, is you divide the terms. And now I'm left with x minus 1. Okay?
Okay.
Now, I can factor this further. This is the part that's a little strange probably that you've rarely done, but whenever you're grouping a cubic function, whenever you're solving it by grouping, you're always going to factor out the binomial term. There's the x minus 1 and there's an x minus 1. So that ends up
Okay.
being the greatest common factor. So it's x minus 1, and what's left over?
X squared minus 2.
And that actually is not an irreducible quadratic. This is something else, maybe new for you. You don't actually have to have difference of perfect squares. That's x minus square root of 2 times x plus square root of 2.
Okay.
Okay, anything, that can be used for anything. If I told you I had x minus 7 and you had to factor it, well, that's the square root of x minus the square root of 7 times the square root of x plus the square root of 7.
Okay.
Anytime you have subtraction basically going on, you can apply this difference of perfect squares factoring method. It's really called the difference of squares. It's only called
Okay.
the difference of perfect squares when you're in lower math. Once you get to the math you're in, they should be calling it just difference of squares. And they don't have to be perfect. So now this whole denominator up here, I can rewrite as 3 linear factors. And that's going to make things easier because now when I go to do the right side, I won't have to use the bx plus c. You only use that if you're looking at an irreducible quadratic or higher, I suppose. So this thing is going to be equal to a over x minus 1 plus b over x minus root 2 plus c over x plus root 2. In other words, I don't need any x's in my numerator.
Okay.
Okay? Now, let's see. When I go to multiply, or when I go to add all of these, let me do it this way. This technique is not one I've always used, but I'm loving it more and more when I use it. And that is to write the common denominator down here. And then what goes up here is going to be a times these two things.
Okay.
X minus 2 times x plus 2. And now if you examine that, you can see that we have not changed this fraction. It's still a over x minus 1. Whoops. I put the square roots in there. Okay, that's why I like this technique, is because it's really easy to verify that you didn't change the fraction. Okay, and that same common denominator goes here, only the top's going to be b times x, times x minus 1 times x plus root 2. And the third numerator is going to be c times the other two denominators, is what you always end up doing.
Okay.
Just to save time, so I'm not spending the whole session writing.
Yeah, no worries.
Okay, and now once again, the denominator is going to be the same as this denominator, therefore this numerator has to be the same as x. So I can now say that x is equal to, let me think for a moment whether it's going to be worth multiplying those two things back together again to give you x squared. I don't think so. We don't want an x squared. We want an ax minus root 2a. Ooh. Hold on. I guess I'm going to have to multiply them back together again. Think for a second here. Maybe our x squareds are all going to, we know there's no x squared term in that numerator. So whatever x squareds I end up with over here, I know their coefficient has to be 0.
Oh, okay.
Okay, so let's put those two things back together again. And that was x squared
minus 2.
minus 2, so it's ax squared minus 2a plus these, that's going to be, let me multiply those two together first, which is, that's x squared minus root 2x minus, plus root 2x minus x minus root 2. And finally, if I multiply those two together, it's going to be c times x squared minus root 2 x minus another x plus root 2. All right, so we want to combine all of our x squareds.
Oh, wow. What's that? No, I was just looking at it.
Yeah, well, let's see if I can do it a couple steps at a time here. So we're going to have a plus b plus c times x squared, correct?
Yes.
Parentheses around that. How many x's do we have? Let's see. We have a plus root 2x minus x. We have a minus root 2x minus x. I'm going to have to multiply these two together. I'm not sure what that's going to look like.
Don't the root 2 bx's go away?
No, because this over here is going to be a c root 2.
Oh, it just becomes...
Yeah.
Okay.
Let me go ahead and write that down here. So we have cx squared minus c root 2x minus cx plus c root 2. Now I've taken that term, my ax squared term, and that term already out over here.
Mm-hmm.
Now, what can we do with our x's? Let's see. I'm going to work over here in this window right here. How many x's do we have? We have root 2 bx. We have minus bx. We have minus c root 2x, and we have minus cx. So if I factor everything, if I factor the x out of that, then I've got this.
Okay.
Yeah, let me just write it like this. Okay, I think that's all my x's. So that takes care of that term, that term, that term, and that term.
Mm-hmm.
Finally, so I know this has to be 1. And I know that a plus b plus c has to be 0. This coefficient has to be 1. And finally, what else do I have here? I have minus b. Sometimes I hate Windows 10.
No.
Hold on. I'm not sure I know. Here, I know how to do it. All right. Let's see. And finally, for a constant, I have minus b square root 2 plus c square root 2.
Okay.
And I know that has to be 0. So here's what I think I have. A plus b plus c has to equal 0.
Mm-hmm.
Root 2b minus c root 2 has to equal 1. And minus b root 2 plus c root 2 has to equal 0.
Yeah.
Well, we have 3 equations and 3 unknowns. We should be able to solve those.
Okay.
I can do a little factoring. I can factor a B out. I can factor a C out. Do I need to is the question. I can certainly divide those. So I have minus B plus C equals 0, so minus B equals C, so B equals C.
Okay.
Based on equation number 3. And the second equation is all B's and C's, so let's substitute C for B. And that, in other words, if I substitute each of these B's for a C, now I've got a C root 2 and another minus C root 2. So what I'm left with is minus C minus C. So I got minus 2C equals 1. C equals negative 1/2.
Okay.
B equals negative 1/2. And A must be positive 1. In other words, now I can solve for A. That should be your 3 solutions.
A equals 1, B. Okay, yeah.
Yeah, then A plus B plus C equals 0. Yeah, that should work. Now, you're always going to have a question of how much time do you spend proving that that's the correct answer. We came up with 1 minus a half and minus a half for A, B, and C.
Okay.
Okay. Now, just for your information, you probably want to know, why is this important? Why do you need to be able to do partial fractions? This is crazy. Well, when you get to calculus, you cannot integrate something that looks like that because you have 3 things being multiplied on the bottom. What you can integrate quite easily is stuff being added and subtracted. I can integrate this term by term. So separating this out into these 3 terms, now I can easily take the integral of that, that, and that, and I'm done. And so this technique offers a way to do these integrals, and that's the only use of it I know of. There is absolutely no use for partial. I had an 8th grader once getting partial fractions in 8th grade. I wanted to strangle somebody just because I'm pretty convinced that there's no use of it other than in integral calculus. So anybody that's not someday going to take integral calculus probably doesn't need to be learning partial fractions. But you probably will be taking calculus, so it's useful for that. And that's its only use as far as I know. And I guess if you have something greater than an irreducible quadratic, like if you had you haven't had any problems like that though, right? I mean, the toughest you've had is the x squared plus 1.
Yeah.
It cannot be factored, so that's why it's called an irreducible quadratic. It can be factored using imaginary numbers, but you do not bring in imaginary numbers into this. When you have an irreducible quadratic as one of your factors in the bottom, you take care of it by putting the bx plus c in a single term in top.
Yeah.
And I don't know what you do if it's an irreducible cubic or something like that.
No.
Well, actually, cubics.
I think you do long division.
Well, you could factor. Cubics, if you had something, you could factor it based on the sum of perfect cubes. In other words, if you had x squared plus 1, that actually has a solution. The solution is minus 1. That's not even irreducible. So, yeah, but I suspect you will not get, even in calculus, I haven't seen anything as hard as a cubic in the denominator. So I don't even know how to handle that. But I've certainly done these problems where you have a quadratic in the denominator and you have to use the bx plus c. But
Okay.
we've done that. So
Yeah.
and I think we did this one correctly. Do you have answers?
Yeah.
If you have answers, why don't you look and make sure, and that'll save us
It does.
work.
Yeah, I checked the answers. This was the answer.
Okay, cool. All right.
Thank you.
Yeah.
Okay. Next problem.
Yeah, what else we got?
This one is different. It is x cubed plus 2x squared minus x plus 1 over x squared plus 3x plus or minus 4.
This is the one you have to do the long division on.
Okay.
Okay. And I'll show you why. Yeah. So how do you divide that polynomial into that polynomial?
You have to find the multiplier that multiplies the first term of the denominator into the numerator.
I don't think it's that complicated. I was just looking at that cubic to see if we could factor it by grouping, and we cannot. And we could factor this over here. That's x minus 4 times x plus 1, or x plus 4 times x minus 1. But you still have to do the long division. What you do is rather simple. You take the x squared and you divide it into the x cubed. X. Okay? Then you multiply that x times all three terms. Now you subtract, just like long division.
Okay.
That becomes plus 3x. Bring down the constant. Repeat. Well, x squared goes into minus x squared minus 1 time. Multiply the minus 1 by all three terms. Subtract. You get 6x minus 3, which is the remainder. So this answer is x minus 1 plus a remainder of 6x minus 3 divided by x squared, the divisor, which can then be factored into x plus 4 times x minus 1. Well,
Okay.
we don't need partial fractions to handle that, and that's a plus sign between the quotient and the remainder. All remainders, whenever you get a remainder, the remainder is the remainder divided by the original divisor, and it's added to what you already had. Okay, and this becomes pretty easy. In other words, we haven't done anything this easy yet in terms of the partial fraction aspect of it. Let's go through this, because there's one technique we can use on this that we haven't talked about yet. Yeah, let me write it. And then this is pretty interesting technique, actually. Definitely one you should know, because you use this technique everywhere except on the really hard ones.
Okay.
Okay, so let me scroll down here so I have a little writing space. And now that's going to become a times x minus 1 plus b times x plus 4. And all of that has to equal 6x minus 3, right?
Yeah.
I guess you can't use that other technique. Let's just hypothetically, so I can explain it to you.
Okay.
Hypothetically, say that that's a 3,
Okay.
having an x in it. Okay? Now, what I'm allowed to do here is this has to be a true statement for all x, right?
Okay. Yeah.
So I can pick x of 1, which takes my a term out, and I end up with 3 equals 5b, and I've solved for b.
Mm-hmm.
In other words, I don't have to use simultaneous equations if I have this kind of a situation. And
Okay.
likewise, so b would be equal to 3/5. And at the same time, I can choose, if I wish, to make x minus 4, which will eliminate the b term. And then I have 3 equals minus 5a. And so a equals 3 divided negative 3/5. And so in this particular situation, I was able to solve for a and b without doing simultaneous equations.
Okay.
In our problem here, because we have this x up here, then I have to go back and do it the other way. I don't know, maybe I do, maybe I don't. Let's see. No, I don't. I can use this technique. I'm going to let x equal 1, okay?
Okay.
What that leaves on the right side is 5b. What's it leave on the left side? 6 minus.
Um, 6 minus 3 equals 3. Oh. Huh.
And so now I've just solved for b.
Okay. And b equals 3/5.
Yeah.
Hmm.
That's a little suspicious, isn't it? Because
Yeah.
it's equal to 3/5 when I didn't have that 6x there. And it was a plus sign. Well, now if I go over and I let x equal minus 4, it's going to take the b term out. So I'm going to have minus 5a equals, well, when x is minus 4, this becomes minus 27. Well, that's comforting. A didn't come out to be the same. A
Oh, okay.
27/5. And there's that does work when you have an x on the left side.
Yeah.
This maybe is more confusing to you. In other words,
A little.
what I also could have done was distribute this, gather my a plus b, and know that it has to equal 6.
Yeah.
Notice that my a plus b does equal 6, the way I did it.
Oh, okay.
Okay? And I would also be left with a minus a plus 4b, and that combination has to equal minus 3. And so that would allow me to solve for b also. Or, I forgot.
Mm-hmm.
I lost my train of thought. But the key understanding is that this has to be true no matter what x is. I could let x be 100, and this has to be a true statement.
Okay.
Okay? The fact that I choose to let x equal 1 is convenient because it makes the a term go to 0 and leaves me with some number of b equals some number, which allows me to solve for b. And
Okay.
choosing to let x equal minus 4, going to get rid of the b term. Now I have some number of a equals to a number, and it allows me to solve for a also.
Okay.
Is this the correct answer? I'm sure that,
Yes.
yeah. But notice I did not do it by simultaneous equations. Whether I did it in a harder, this is actually the way
I
my
think
book,
that way was actually easier.
what's that?
I think that way was actually
I
easier.
think it is too, and this is the way the books do it. The way I just did it, where I let x equal 1 or I let x equal -4. This technique cannot be used for all problems, though, and I don't believe it was usable in the previous couple problems we've had. Sometimes you do have to distribute, gather all your x terms, equate coefficients. In other words,
Okay.
sometimes you need that method and you end up with a couple of equations or 3 equations. We ended up with 3 equations and 3 unknowns. But a lot of the times you can use this method here, even if there's a third term. Let's say there's a third term, which is that. Well, now I'm going to let x equal -2 to get rid of the c term, and at least that'll give me an equation about a and b.
Yeah.
So, and, all right, what else?
Yeah. I think this one's a big problem.
Back up there a little bit. Our answer was x -1 plus those partial fractions, a over x plus 4 plus b over x -1.
Okay.
Okay?
Okay.
You understand what I'm saying?
Yeah. I get what you're saying. I just had to look at it a little bit.
Yeah, in other words, we broke that down, we broke just this down into a over that plus b over that.
So the answer equals x -1 plus a over that and b
Yes.
over that?
Yes.
Okay.
Yes. Plus b over that. In other words,
Yeah.
all you're doing, you don't need to do anything with the x -1. It's no longer in need of partial fractions. But this part is.
Okay.
The remainder part. That's kind of interesting, really. You've had enough precalculus that you know what slant asymptotes are?
Yes.
Well, here's what's funny. This is the equation of the slant asymptote for this problem.
Oh, really?
Yeah, if I gave you this cubic divided by this quadratic, the way I figure out the asymptotes are do the division, take the linear factor, that's the equation of the asymptote, and discard the remainder. You don't care what the remainder is. The only thing you care about is that linear factor, because an oblique asymptote is always a straight line. It's never a curved line.
Huh.
So what's ironic is in this problem, the only thing we care about is the remainder, really, and we don't care about this factor. So here we have two different math problems, one where you care about the factor and you don't care what the remainder is. Although this remainder does determine your vertical asymptotes in that case. In other words, this problem right there has a oblique asymptote and it also has two vertical asymptotes because x still can't be equal to -4 or +1.
Okay.
Okay. So you'd have a strange grid to plot your original function on. But
Okay. Well, that's cool.
and you only generate the oblique asymptote if the numerator is exactly 1 degree higher than the denominator's biggest x. So having x third to the third divided by x squared is the perfect scenario where you know you're going to do that division and the linear factor you get is the equation of the oblique asymptote.
Okay.
If it was x to the fourth, I don't know what you do.
Huh.
I really don't. I've never seen that problem in a math book. In other words, you can't just do the division because you're going to end up with an x squared in the numerator, and that's not going to be an oblique asymptote. So yeah, I don't know what happens if it's x to the fourth in the numerator and x squared in the denominator. But you're not going to see that problem. You're going to see problems where it's occasionally one size bigger only.
Okay.
All right.
Okay. Next problem is, okay. 1 over
Hold on, it seems
x.
just a second.
Oh, okay. No worries.
Well, my pen disappeared. Hold on. Sometimes I have to actually unplug my tablet and plug it back in again. Let's see if I can do it without closing out this. Yeah, that worked. Cool.
Cool. Okay.
1
So
over.
the next 1 over x times x plus a.
Okay. That's not the same A as what we've been using. So I'm not going to use the letter A.
Okay.
I presume that that's not the same A.
No. Yeah.
In other words, I don't want to put A and B because then our A's are going to get confused. And it doesn't
Yeah.
matter if I use A, B, C, D. I could use P and Q here.
Mm-hmm.
Okay. The fact is that I know that I'm going to split it up into two fractions with these two denominators. And now I've
No.
got B times X plus A plus C times X. And that has to equal 1.
Okay. So that becomes bx
Yeah, I guess
plus
that's all we can do. Yeah.
ba plus cx equals 1. So
That becomes X times B plus C, putting the coefficient in front, plus
okay,
BA.
plus ba equals
There's
1.
no X term in that.
So then we just put a 0.
So I know that B plus C equals 0, so B equals negative C.
B equals 0, so b equals negative c. And
And
then b,
BA has to equal 1. So negative CA has to equal 1. I'm not sure I've ever seen a problem like this, and I'm not sure I know how to do it. Can we get anywhere from this?
I don't know.
You'll see. If BA equals 1 and CA equals 1.
And this one was one she didn't give us for an answer on this was like the challenge problem.
Oh, wonderful. Yeah. The one
Yeah.
that we truly need an answer.
Huh. I know.
Because sometimes if you have an answer, you can figure out how to do it.
Yeah.
Maybe this is enough. Let's see. No, I've already substituted. I don't have 3 equations and 3 unknowns. I got 3 unknowns, A, B, and C, but I can only come up with 2 equations. And let me think for a moment. Let's see. If, this might work. That technique I was using, let's try that. Let's see if we get anywhere with that. Now let's cross that out for a moment.
Okay.
If I let x equal minus a, it'll take the b term out, and we'll have minus a times c has to equal 1. If I let x equal 0, then I've got b times a has to equal 1.
B A equals 1. Okay. Huh. Can we go anywhere from that?
Well, I know c is equal to minus b, but again, I've got 3 variables and only 2 equations. So, maybe one other spot we can go here. And that is, you can let x equal anything you want, and we've let it equal minus a and 0. What if we let it equal to 1? Then we would have...
Isn't it b plus ba plus c?
And then that would have to equal 1. And that might be our third equation.
Okay.
Let me think. I think that is. In other words, we now have 3 different equations. I believe they're different. This is, let's see, so this is 1 equals b plus ba plus c. Let's write it like that. And now let's see. The fact that BA is 1, I can replace that with a 1. Now my 1's cancel, and I end up with B equals minus C.
1 plus c. Huh. I think that's as far as we can go.
Well, if B equals minus C, huh? Oh yeah, because if I plug in minus C, now I just have 2 equations that look the same. In fact, I could have gathered that information from that.
Yeah.
You need to make up a third number and generate a third equation. It turns out I don't think that it's an independent equation. Hold on a second. If A is equal to 1 over B, and I plug in 1 over B for A, then I get C over B equals 1. I'm almost beginning to think that this A was that A, like that.
Okay.
Is it possible that that could have been, in other words, he intended to use the variable A to be the same as that A?
I think so, because you're supposed to go in order, like, of A and B.
Okay.
So
Well, if
that could
this
be
was
it.
the problem, notice that now it's going to be really easy to solve. We don't have 3 variables anymore. Or do?
No, yeah.
We have A times X plus A, and we have B times X. And now I can let X equal minus A. So I get minus BA equals 1. And then if I let X equal 0, I get A squared equals 1.
Okay.
Which means A equals 1. Oh no, A equals plus or minus 1. Plus or minus 1. And A has to be minus 1 for this one to be true. So that's minus 1. And B has to be
Negative.
plus
1. Okay.
Okay, so that should be our answer, and it should be relatively easy to check. Yeah. In other words, this would give you negative 1 times x plus a plus x, and that's minus x minus a plus x, which leaves you a minus a. A is minus 1. Everything works.
Cool.
If a is minus 1. So assuming that's what your teacher meant, then this is the way to solve it. And if they meant that as a third variable, I'm not sure we can solve it.
Yeah.
I'm not sure we can ever get more than 2 equations and 2 or 3 unknowns, and you cannot solve that.
Uh-huh. Yeah. Okay. Cool. Well, that was the last of my homework problems and last that we learned in class.
Okay.
And so then on Monday I'll get a review and I'll have a quiz on Wednesday.
Okay.
And
So
then on my last quiz I actually did better. I got an 85 out of 100, so that's 85%. So B.
cool. Good.
Yeah.
Glad
Mm-hmm.
glad to see you making a little progress.
Yep.
Yeah, that's great. All right. So I will meet with you Monday at 4. Now let's see. Did we make that regular? Or I think in this case you actually signed up for that one. Yeah,
I think we signed up for that one.
okay, and you're signed up also for next week, both Monday
For
and
Thursday.
Thursday, but not the following one. In
Yeah.
other words, that was not a permanent appointment, whereas the one on Thursday I think is. No, it's not even. Um, so
No. Can we go back to next Monday though for a second?
yeah,
Because I know next Monday I have something with lacrosse.
okay, that's also Halloween.
Yeah, it is. And you don't want to be booked.
Not that that would affect me. They don't start showing up at my door until 7 o'clock. So
Okay, so could we maybe do like 6 p.m. and change that actually?
sure. Well,
Thank you.
yeah, no, it's really easy for me to move it on my end.
Cool.
Not so easy for you. Incidentally, the way you do cancel an appointment, you know how when you schedule one online, you get an email confirmation right away?
Yeah.
You go to that email confirmation, there is a cancel link on that thing.
Oh, okay.
And if you hit the cancel link, it will cancel that session. And then you can reschedule another session. So
Okay.
if you want to reschedule something without my assistance, that's one way to do it.
Okay.
I don't ever have any problem you calling me and I'll do it. But okay. And then we'll leave the week after that alone for the moment.
Yeah, for the time being. My mom's in Hawaii right now, so when she gets back, I'm sure she'll like see what days and like what's good.
Lucky her.
Yeah. Actually, my whole family lives in Hawaii.
You're kidding.
Yeah.
Wow.
So,
So you visit there a lot, huh?
I'm not sure if she told you, my father's a pilot,
Oh, no.
so it makes flying really easy for us.
Wow. That's funny. I have another student whose dad is an international pilot also.
Huh, that's cool.
Yeah, his name's Mike Stapp.
Mike Stack.
I'm sure there's thousands of pilots, so it's unlikely your dad's going to know him. But
Maybe.
my dad used to be stationed in Hawaii for 3 years, so when I was just out of college, I got to go there lots also.
Oh, really? What island?
And he was in the military, so I got to fly cheaper also. There was always those space available flights that didn't cost you anything.
Yeah, those are awesome.
But I
Do you know
love
what island were you on?
favorite place in the world. He was stationed on Oahu, and then I went on a honeymoon to Kauai
Oh,
10
Hawaii's
years
beautiful.
later, and then I went to Maui and spent a few days there also. I think my favorite is Maui, maybe. Yeah.
I've never been to Maui just because we don't have any family on that island.
Uh-huh.
But I've been to Kauai and I've been to Oahu in the Big Island, but Kauai is beautiful.
I've never been to the Big Island, and when I went to Kauai, it was shortly after they'd had that huge hurricane, and so
Oh, really?
everything was messed up pretty good. Yeah, the
Oof.
rainforest looked like somebody had come by and blown everything down, almost. But
Hmm.
um, they say Kauai is supposed to be the most beautiful of the island.
Yeah.
That's what
Maybe not after the hurricane, but
yeah, that's what they said before the hurricane hit.
it's
So
funny.
anyway, but that's cool, having family in Hawaii. I've always thought that that was the prettiest place on earth that I've ever been to, at least. So
Yeah,
yeah.
it's a place.
All right, Nicholas. So I will talk to you at 6 o'clock next Monday.
Yep.
Talk to you then.
Okay, thank you. Bye.